So the ancient Greek mathematicians did a number of things well. Two of the things they did really well were number theory and geometry. Number theory didn't have much practical use, at least in those days. Geometry had a great number of practical applications. But in any case, into both of these branches of math, the concept of infinity was woven, at least in rudimentary form and implicitly, if not explicitly, and with a great deal of insight, if not yet with the formalization that would come in the centuries to follow. My first example of infinity coming into play is from the field of number theory, in particular dealing with prime numbers. 2,500 years ago, those old Greeks noticed something about numbers. You can bust most of them up into factors, like that, or like this. Some numbers can't be busted up. The only thing that goes in 13 is 1 and 13. The ones that nothing goes into, except themselves in 1, are called primes, and the ones that can be busted up into smaller numbers are called composite. Any composite number can be broken up into smaller factors. There's nothing to stop you from keeping on until you can't break the factors down anymore. And that means that any composite number can be busted up into primes. And that means that if you can't find any prime, if there is no prime that goes into a number, it must be prime itself. So one fine Greek afternoon about 2,300 years ago, a fellow named Euclid thought about stuff like this. Pretty soon he came up with what I'm going to show you. Of course, he did think in Greek, not in English like me. And he didn't really say there was, quote, an infinite number of primes. He just said, quote, prime numbers are more than any assigned multitude of prime numbers, meaning you could always find one more. And to tell the truth, he didn't prove exactly what I'm going to do, that there's always a bigger one. He just proved that there's always one more. But the core of his argument is exactly what I'm going to show you. So suppose you come up to me and say, I found the biggest prime there is, and I'm going to call it LP for the largest prime. I'm going to give you something back. This number, 2 times 3 times 5, etc., up to whatever you gave me. I list all the primes down, times them all up, and add 1. Okay? Those dots means I have all the primes filled in up to what you told me was the biggest one there was. I'm going to call my number RBN for a really big number. Now, something about this number I want you to see. Suppose you divide 2 into it. 2 is going to divide even into this part, and there's going to be 1 left over. And suppose you try to divide 3 into it. 3 is going to go into this part, and there's going to be 1 left over. In fact, you divide any prime you want into it, it's going to go even into this part, and there's going to be 1 left over. That means there's no prime that divides into it. And that means, like we just said, that it is prime itself. So I've got a prime number, and it's bigger than yours. So there. But y'all pretty smart, and you don't give up that easy. You say, now wait a minute here. Reuter, I'm going to give you something back, and it's going to look like this. I'm going to take all the primes up to what you just gave me, and I'm going to add 1. And you run the same argument back again. Every prime there is going to go even with 1 left over. That means your number is prime, and it's bigger than mine. So there, right? Well, we could keep this game going for quite a while. In fact, pretty much forever. You can always find 1 more prime. And whether or not you use the word infinity, it sure seems like we have proved there's an infinite number of prime numbers. Another thing the ancient Greeks did, in a number of ways, they found the area of a circle. And each of these ways involved, to some measure, the concept of infinity, and in particular, the concept of limit. There's one way that I came across. It's pretty darn clever, but it's easy to understand. And Archimedes came up with this about 50 years after Euclid, which is still about 2,200 years ago. Suppose you start, being the observant Greek that you are, by noticing that whether your circle is small, medium, large, or even extra large, The comparison of how far it is around, called the circumference, compared to the diameter, how far it is across, is always a little more than 3. It's a little more than 3 times as far around as it is across. You decide to call that ratio pi. You could have called it Dimitri or Anaxagoras, but you decided to call it pi and you're stuck with it. It's another thing we can say. It's obviously twice as far across as it is, that's the diameter, as the radius is from the center to the edge. That means in place of the diameter we can put 2 radiuses. And with a little basic algebra, you multiply through 2r on both sides. You come up with the fact that the circumference is 2 pi r. Of course, the Greeks didn't actually have algebra with symbols the way we do, but they could do stuff equivalent to this. And finally, you say to yourself, look, it's 2 pi r the whole way around this circle. I bet you that it's 1 pi r if I go halfway around. So I want you to hold that thought now. You have a flash of inspiration from Olympus, perhaps. You say to yourself, all right, self, suppose I cut a nice round pi up into 4 pieces like this here. And suppose I rearrange those pieces like this. I got something that looks a little bit like a box. If you take the top 2 round measures, that's halfway around the circle. That's pi r. If you take what sort of looks like a slanty side of a box, that's r. That's the radius. And suppose you take 8 pieces instead of just 4. Rearrange them. Well, that looks a little more like a box. Still, the top 4 put together being halfway around the circle are pi r. And still, the side being the radius is r. Then you take 16 and do the same thing. By the time you get up to about 32 or 64, it sure looks a heck of a lot like a box, where the top is still pi r, being halfway around the circle, and this side is r. Well, you know what the area of a box is. It's length times width. Again, that's the r for the width and the pi r for the base of it. The more pieces I cut my pi into, the more it looks like a box when I rearrange them. And since the box is made of exactly the same pieces as the circle, the area of the circle must be exactly the same as the box. That's length times width, that's pi r times r, and that's pi r squared. So it was shown that the area of a circle is in fact pi r squared. As you can see, this argument relies on increasing the number of pieces indefinitely, and it relies on the idea of one figure approaching another. That is, the idea of limit, which is one of the number of contexts in which infinity comes into play. Now, finally, I'm going to talk a little about Zeno's paradox. The Greeks did have the ideas and the concepts of infinity. They had insights into it, but they didn't have a clear definition. Zeno came up with this apparent dilemma regarding Achilles and the tortoise. Not much of a contest, you may be thinking. However, Achilles, in full body armor, knew darn well he was twice as fast as his tortoise was. Being a good sportsman, he decided to give the tortoise a 1 stadia head start. By the time he got to where the tortoise was, though, to his dismay, he found that the tortoise was half a stadia from where he'd been, and still ahead. Achilles was, in fact, one heck of a warrior, but as far as being bright, maybe not so much. Well, by the time he'd gone that half stadia, darned if he didn't find the turtle had gone a quarter of a stadia ahead of that. And every time he got to where the tortoise used to be, it had gone a halfway farther than that. Well, it seems, viewed from that point of view, that the poor guy could never catch up. But Zeno knew, just like you all know perfectly well, that in real life, Achilles would in fact win, and it shouldn't take him too long to do so, hence the paradox. Reduced to the mathematical skeleton, the problem is that apparently this sequence, a half plus a quarter plus an eighth plus on so forth forever, maybe that just doesn't have any realistic meaning to it. But viewed from another perspective, it seems the sum of an infinite number of positive numbers should in fact have a very clear and obvious meaning. In other words, if you take the numbers a half, a fourth, an eighth, and a 16th and keep on going, say you walk, say this represents me walking halfway to that wall, and then a quarter more means I'm halfway from there, and an eighth would mean I'm halfway from there. And suppose I keep on doing that pretty much forever and add up all my steps. Well, it's pretty clear where I ought to end up. I ought to end up at the wall. On one hand, I can get as close to it as I want. On the other hand, doing this, I'm never going to go past it. So it seems like this series of numbers ought, in fact, to simply add up to 1. And that's what later mathematicians did. They simply defined this sequence, an infinite sum, to be equal 1, and towards resolving that paradox. At any rate, on the ancient Greeks' mathematical and geometrical struggles and accomplishments, through the centuries to follow, mathematicians began to build the imposing edifice of present-day mathematics that some of you enjoy and some of you are forced to endure. As through the centuries, these concept of the infinite became ever increasingly formalized and refined, and not to mention visualized. A little infinite regression. To regale you with these further developments, I give you my distinguished colleagues, Dr. Chris Martin, who will set out for you some of the general advances in the language and concepts of math from the 13th through the 18th centuries, and Professor Loris Zuka, who will show you how infinity came back into play at a level significantly more sophisticated than that of the ancient Greeks. And I do trust that however you felt about my presentation, you will not find these gentlemen's presentations all Greek to you. Thank you.
Well, welcome to the 13th century to the 18th century. A lot was going on from the Greeks and the Romans. The problem was, in Europe was in the Dark Ages. Math was fairly stagnant in Europe, not much was going on. A lot of great mathematics, though, was being done in Persia, China, and India. Europe, though, was stuck with Roman numerals. Oh wait, we're still stuck with Roman numerals. We have clocks, but we kind of get used to reading them. It's pretty hard to remember your girlfriend or boyfriend's date they put on the band if you can't read Roman numerals. How about bingo using Roman numerals? We'd be calculating all day. How about class t-shirts? Don't you want to represent class of 2011? Probably not that way. What about adding them up, trying to figure out how do you add up these X's and numbers? Kind of tedious. So what mathematics needed in Europe was a language. How do we represent numbers? Well, there's a lot of choices that we could pick from. I'm not real clear about the tie. I don't know if I could get which way that the circle went to remember. Indian and Mayan, not too bad. Babylonian always looked to me like a bird scratching in the mud, but so we had a lot of choices for things other than Roman numerals. In the 12th century, Leonardo of Pisa had a brilliant inspiration. He said, why don't we quit using Roman numerals? Why don't we use the Hindu Arabic numerical system of 1, 2, 3, 4, 5, our current system of numbers? There's a problem though. The Crusades were on. Islam was not in such a great favor. And so in 1299, these numbers were actually banned from use in Florence, Italy. It wasn't until the 15th century that we finally got to use the numbers that we use today. Fibonacci also did some interesting things during the Middle Ages. It was a boring time, so he watched rabbits. So if I have first a pair of 2 rabbits, cute bunnies, give them a little time to mature, takes a month to mature. After a month of maturing, we now have 2 pair of rabbits. Pretty soon we have lots and lots of rabbits. And what he came up with was an infinite recursive sequence, where if I start off with one pair and one pair, 1 and 1 adds to 2, 2 and 1 adds to 3, 3 and 2 to 5, and so on. And you actually get this recursive formula, which is the sum of the previous two numbers. Now you might think, well, the guy's kind of a weirdo and bored, but these Fibonacci numbers occur often in nature. You have flowers with 2 petals, 3 petals, 5 petals, 8 petals, 13 and 24 petals. These numbers do pop up in random, strange places. Math during the Middle Ages was kind of mysterious, and some people found in it alchemical and magical meanings. For example, this was a time of magic squares. And so the square that you see in this top corner here, if you add up all the rows, or add up any column, or the diagonals, you end up with 34. Now, if you also look at the other combinations that also give you 34, you get these interesting patterns. It's kind of interesting that randomly you get these patterns making up these kinds of pictures. So perhaps there is a magic. I don't know. But after we have all this nice math, we have numbers, how do we tie them together? We need some symbols. Our familiar fraction bar with writing A over B wasn't even thought of until 1202 by Fibonacci. The symbol for plus and minus, not till 1489. The decimal point, we write that all the time, didn't come about until 1492. So all the language that you see in mathematics took some time to develop. The dot for multiplication, the cross for multiplication, and so on. There was a professor here, Scott Nelson. He used to always see me in the hallway and ask me, was I still looking for X? The answer is yes, I am still looking for X. And maybe one day I'll find it, but there are others looking for X too. Pooh and his clan is looking for X. Even the president in his spare time is helping us look for X. If we start off simply looking for X, we have something that's called a first order equation, which is just a line, something like y is 2x minus 4. And setting it equal to 0, we're just asking, where does this thing cross on the x-axis? Turns out there's a way to do it. There's a formula for it. If we go to second order, we're still looking for x. Second order has a squared on the variable, making it second order. This poor guy's looking for x. Second order equations look like that, but luckily there is a formula to tell us how to do it. Most students don't like it, but there is a formula. We keep on looking for x, and someone thought, well, what about the third order? Well, in 1535, there was Mr. Tartaglia found a formula for third order equations. There was a formula. In 1545, Cordano found a formula for fourth order. So there's a way to plug in all those numbers and get an answer. But I have to tell you, there is some gossip. It's rumored that around 1490, fourth order was solved. The problem is that was the time of the Inquisitions. The mathematician was summoned. He was told it was not the will of God to know fourth order and was burned. That's just rumor, according to Wiki. What about fifth order? Well, fifth order came along in Galois. A young man in his 20s looked at this particular problem, jotted down ideas about it, jotted down all of his ideas. And what he was able to prove is, guys, quit looking for a formula. There is no formula for higher than 5. Not that we can't find a formula, there can never be a formula. Not that we can't construct one, there just won't ever be one. It always has to be solved numerically. Now the problem with Galois is he was a young man, he was in his 20s, and one night he jotted down in a letter all of his knowledge of mathematics, which was quite extensive, in a letter to his friend. The reason he jotted it down in a letter to his friend is the next day, he had a duel coming. Well, to say the least, Mr. Galois was a better mathematician than he was a duelist. He did not survive the duel and died the next day. But we do now know there is no formula. The Egyptians and the Greeks loved to gamble, but no one had ever systematically written down how do we determine and specify randomness. What does it mean to be random? Well, we can roll dice, we can flip coins. We need some way to talk about random things. In probability, we have something called a sample space, which is just a collection of particular things that can occur. E is an event, which is a sub-collection. And then we can count up how many things are in there. So theoretically, we jot down the probability of an event is this particular ratio of numbers. In reality, though, let's say I take a coin and I flip it 100 times. And I keep track of the number of heads and tails. Well, I might get 49 heads, 51 tails, giving a probability of heads of 0.49. I might do it 300 times and the number changes a little. I might do it 500 times and the number changes again a little. What they determined is if we flipped the coin an infinite number of times, the theoretical probability would make it a 50-50 chance. We still use probability every day in our real lives. We look every morning for what's the probability of rain. You may not have thought about it, but the probability of not rain is 1 minus that probability that you read, or 70%. So the probability of any event is always a number, and that number is stuck between 0 and 1. Now, if NASA had only considered probability a little bit closer, that might have helped. When NASA built the solid rocket booster, they looked at each joint of the solid rocket booster, and there was a 96% chance of that joint not failing. The problem is, what happens if you have 6 joints in a whole system? Well, then it becomes 0.96 raised to the 6th power, and the probability now of not failing is down to 78%. Some of these kinds of things were implemented after the first Challenger accident, and they considered these kinds of things in more depth. How do we locate an infinity of points? Well, Descartes in 1637 developed a coordinate system. So we can talk about how do we locate points in space. In 3 dimensions, it's a rectangular system. We have a cylindrical system, another way to measure where are things. We also have a spherical system. Mr. Fermat is probably the father of modern number theory. And he puzzled mathematicians for a very long time because he scribbled a little note in the margin of his book. He said, if I have a to the n plus b to the n is c to the n, this thing is not solvable if the n is bigger than 2. Now, clearly it's true if n is 2, because you can see 5 squared is 4 squared plus 3 squared. It took 350 years, and let me backtrack and say Fermat actually wrote in the margin of his book that the proof was trivial, but he didn't have time to jot it down. It took 350 years. It took Andrew Wiles at Princeton 7 years of work, of lots of failures back and forth, but in 1993, he finally proved that particular conjecture. What about if I had something from music, namely standing waves? I make a standing wave with one wave, chop it in half, I get a half, chop it again in third, I get a third. What happens if I take 1 plus a half plus a third plus a fourth and add all these numbers up? Do I get something nice? This infinite series, the answer is no. It adds up to infinity, even though you are adding up a smaller and smaller amount. What about the bouncing ball problem? Got a ball. Throw it up in the air. The ball bounces. Each time it bounces up a particular height back up. How far does the ball go? Far enough. So let's see if we start off at a height h. We're going to drop down, bounce up half the height, bounce down half the height, a fourth the height, and so on. It turns out you can sort of group the numbers and play with them a little bit, but what you get is an infinite geometric series. And the bottom line is the ball bounces 3 times the original height when all is said and done. Then we finally got to calculus, and we have the royal battle that will never be solved between Newton and Leibniz. Each claimed that they developed calculus. It's never quite known who actually did. They both had major contributions. One of the questions in calculus is if I have a curve, how do I find the slope of a tangent line? Well, if I do normal math from algebra, I've got 2 points and I've got a slope formula. But what happens if the point gets shrinking backwards and I only have 1 point? What happens to my formula? How do I reformulate that? Or said a better way, how fast do we motor along the graph? The other big topic in calculus is integration. Integration is this S. The symbol for integration looks like this elongated S that's stretched out. Well, S, why S? Well, because we are summing up an infinite number of things, an infinite number of contributions. In this case, I'm summing up the number of things under the curve, and I'm trying to add up those areas. It turns out the area under that curve is 2/3. This area also comes about in terms of physics. How do I measure the work of something? Well, I'm summing up the force as I push an object along. We get closer to modern mathematics, and we have strange objects in terms of topology and algebraic topology. We have this thing called a Mobius strip. All I do is take a normal strip of paper, and instead of joining it normally, I put a single twist in it. If you do this in the privacy of your own home and use your pencil, what you'll find is this particular object only has one side. There are not 2 sides there. Even stranger, it only has one edge, not 2 edges. And finally, the Klein bottle is even stranger in 3 dimension. It has one side, there's no inside, there's no outside, and there are no edges. Mathematics had to look at strange things. These included, and later up to present day, they began to see patterns in things that were not seen before. And Professor Zucca is going to continue and talk a little bit about the strange modern things that mathematicians discovered.
Today we talk about fractals and chaos theory whenever we want to talk about infinity today. A fractal basically is any object that is self-similar at any scale. Okay, so an example of this is in nature. Like if you look at this, this is an example of a certain type of broccoli, cauliflower broccoli. if you look at it, each one of these little pieces in here kind of looks like the whole thing. If you look at this, this is an example of a certain kind of plant. Each one of these little pieces in here looks like the whole thing. The same thing occurs like with a nautilus. The whole thing looks like each one of these little spirals. So if you keep going down deeper and deeper and deeper, you see that it looks like the entire object together. Same thing can be done with ferns. Each one of these little fronds in the fern looks like the whole fern together. Okay? And so you can go on infinitely, theoretically, into some objects, and you will have what's called self-similarity. It's similar at all scales. A tree is another example of it, you might see. If you look at this tree and look at one of the branches per se, each one of these branches kind of looks like the whole tree together. All right? So a fractal is something that is self-similar at all scales. Okay? Now, with a natural object, you can't get down, you know, infinitely close and expect that. But in theory, that's the case. All right. So we're going to start a little game here. Okay, you see a simple triangle, all right? And we're going to make something that looks kind of cool out of this. Let's see if this will work. All right, so we start with this triangle. This is so cool. All right. Imagine there's a person at each one of these vertices. There's a person at A, a person at B, and a person at C. And each person has a whistle. And you have a little dog. And you can put the dog anywhere you want in this picture, all right? Put the dog maybe right here. And suppose that A blows the whistle first. So as soon as A blows the whistle, that little dog runs towards A, okay? And when the dog is halfway to A, someone else blows a whistle. And the dog has to stop and go towards that person. So maybe C blows it next, okay? And halfway to C, someone else blows a whistle. Maybe B blows it next. So the little dog goes towards B. And this thing just goes on forever. In fact, B may blow the whistle again, and the dog keeps going. Maybe the dog starts on the edge, and it goes inside the triangle somehow, okay? All right, so you make this dog do this infinitely, all right? So we'll start the process here. Let's see, let me make the pixels a little bigger. So every time that the dog has to stop and go towards someone else, we're going to put a dot, okay? And so it goes on and goes on. It looks kind of boring. Now, keep in mind that it's completely random who is blowing the whistle. In fact, everyone in this room can have a different series, A, B, C, whatever, and you'll get some sort of object. And the objects you get is that, every time. Every time. It's called the Sierpinski triangle. Now, if you start the dog at right here, there's obviously going to be a dot there. So what you can do is you can erase the first 10 or 20 dots, and you'll get this thing every time, which is kind of bizarre. And the other cool thing about this is that it's a fractal, which is what I talked about earlier. If you look, each one of these triangles here looks like the bigger triangle. And so this thing goes on forever. The Sierpinski triangle basically goes on forever. This is one that's upside down. Which is kind of bizarre, because if you just zoom in and zoom in and zoom in, this thing is self-similar at all scales. All right? So that's an example of something that goes on for infinity. This is one way we look at infinity in the modern world. Okay, so big deal, right? So, all right, it's kind of a cool little math object. What do you do with this, right? So it's actually used in computer animation quite a bit, okay? So here's your good old Sierpinski triangle. And what we're going to do with this is we're going to deform it a little bit, all right? We're going to take it, move it around. I'm going to speed through this little demo. And let's go a little faster, move it around. So what's happening here is we're taking those little people that have the whistle, and we're moving them around. That's all we're doing. And they made them into squares just to make it look bigger. And so if you deform this a bit, it starts looking like something organic. Keep going, keep going. Now we're going to add a fourth one. That's going to make the stem of this thing. keep going, keep going, and basically we've got a little tree out of this thing. And so this is how they do a lot of computer animation. So all those natural-looking trees, clouds, armies of men that you see in some of the Star Wars movies, they're made like this a lot of times, not all. What you have from that triangle that I showed you, which looked like just some useless mathematical but cool object, is something that you see all the time in computer animation. And this is how infinity is used in modern mathematics. Okay, so where does chaos come in? All right, I'll show you in just a second. So remember from college algebra, x squared plus a constant is just some parabola, okay? It just looks like this. If you add 2, it's up 2. If you add 1, it's up 1. If you subtract 2, it's down here, okay? Y'all remember this? All right, even if you don't, this is what it looks like. It looks like this parabola. All right. So what we're going to do with this is we're going to do something a little different. With that x squared plus or constant, we're going to plug in a number, all right? When we plug a number in, 1 squared plus 1 is 1 plus 1, which usually equals 2. Now we're going to plug 2 back into this. So 2 squared plus 1 is 4 plus 5, 8 plus 1 is 5. Now we're going to take the 5 and we're going to plug it back into the original. Plug the 5 in. All right. 5 squared plus 1 is 25. Plus 1 is 26. Okay, and you keep going. You just do this forever. All right. So here's where kind of the chaos and the fractals comes in. And I'll get to this in the next slide. But what I want to mention is chaos theory is the study of chaotic behavior in a seemingly patterned process. So you take something that seems like it's very like not random, and things end up being random. Or it's the opposite of that. You take something that seems like it's random, and you end up finding a pattern in it. Like the dog running between the 3 points, it was a random process, but you got that cool Sierpinski triangle out of it. So you get chaos, a chaotic kind of process, but you end up with a pattern out of that. All right. So anyway, we're going to take this guy, and I'm going to teach you a little bit about what's called the complex plane. And trust me, you're going to see a really cool object in just a second. I just have to get through some of the math. A lot of you guys might have seen in your algebra classes the letter I, it's the square root of -1. Well, if you take a complex number like 5 plus 4i, the way you graph it in the complex plane is the following. You go over 5 and up 4. It's really that simple. A lot of times whenever you do the quadratic formula like Chris was talking about, you get a complex number out of that. And so to graph complex numbers, which it's really a shame that more students aren't taught how to graph them because it's really a cool science. You just take the first number, you let that be the x, and the second number is the y. So back 2, down 3. So if you take this along with this, okay, you get this. So instead of the parabola, that U-shaped figure, you get this guy. About 10 lines of computer code creates this. All right, so you're like, okay, what the heck? So I'm leaving out a little bit of mathematics about maybe doctor's level mathematics in this. But basically you get this, and I can give another lecture on how this is obtained another time. But the cool thing about it is that this puppy is infinite. And I'll show you how. And we're going to zoom in. This is how much we're zooming in. 10 to the 1, so 10 times. Now 100 times. Now 1,000 times. All right. And now 1,000,000 times. We're zooming into the XY plane. Okay? So the original thing was just the XY plane, basically. Now we're zooming in. We're beyond 1 trillion. This thing goes on infinitely. This goes forever. All right? And just never stops. Just goes on and on and on and until you're dizzy or you're high. One of the two. I don't know. Or maybe you're both. All right? So it just goes on forever, pretty much. And so what I've done is I've taken something that normally looks like a parabola in your college algebra class, and I've made it look a lot cooler. In fact, I teach this to my college algebra students if we have time. It's really not hard to create. All right, so There's actually a better one. This one is better. I'll show you. You don't have to just use two colors. You can zoom in on this thing, and what you'll see is a fractal, because look, this guy appears again. And there's other ones, and other ones there. So I'm going to zoom this, I'm going to speed this up a bit. This thing goes on forever. It's going to zoom into that little piece there. And if you notice, there's these little blobs here. These are all the same little object that we started with. So I'm going to zoom in some more, and some more, and some more. And it just gets really kind of cool. And so this thing just goes on forever until infinity and beyond, as they say. So this is a little bit how mathematics is used today. And if you're ever interested, just Google the Mandelbrot set to see where, other versions of this as well. So this is a little bit of how infinity is used more in the modern world. Okay, and this is a little bit beyond calculus, but it can easily be taught in an algebra class. All right, so thank you very much.